So, in this chapter, we start with the ideal gas law and the kinetic theory of gases. So, in this chapter, we apply the concept of thermodynamics on gases. We're first going to be assuming an ideal gas, and we're going to make some assumptions on the gas that we are studying. And then we're going to see the relationship between quantities that we have studied in thermodynamics and the gas molecules and their dynamics themselves. Now, why do we study gases from the first place? So the thing is, we always study thermodynamics associated with gases because gases show us the full interaction in thermodynamic properties. So, for example, we have studied previously that we have a change in the temperature, and then there's an energy Q associated with that, which we wrote as mc delta T. And we also talked about the expansion, so the change in the volume, delta V. We can study the same thing for gases, and one more quantity will show up. So if I have a change in temperature, there's some heat energy, there's also some change in the volume. There will also be a change in the pressure. And there will be some work done, namely gases will be expanding, and as they expand, they can do some work and lift objects, as you can see in the figure here. So in this demonstration, a gas inside a container, here's the gas, is expanding and compressing continuously as it feels the hot and cold sides of this pipe. And as it expands and compresses, it can move around this wheel. This is basically how all engines work: car engines, steam engines, ship engines, and these are also at the heart of the operation of refrigerators and air conditioners. That's why these are of particular interest. We're going to be working on them in this chapter. Before we start working with the thermodynamic properties themselves, I want to remind you of some properties of atoms which we are going to be needing to study gases. Namely, as you can see here, I remind you different atoms have different atomic mass and atomic number Z. Atomic mass A determines the mass of the atom. These are given to you in the periodic table. So if you look at the periodic table, here's the atomic number, here's the atomic mass, and we have an important relationship between these, namely through the number of moles. The number of moles in a certain specimen of material is equal to the number of atoms over Avogadro's number. And this is also equal to the mass over the molar mass. And basically from this relationship, we are going to be using a lot of these quantities as we study gases, because in gases, sometimes we're interested in the number of mole rather than the mass of the specimen itself. And of course, I remind you, in atoms, if I have atoms will have different molar mass than molecules. In molecules, you will have to calculate. So as you can see here, hydrogen has an atomic mass 1. And if I study water, on the other hand, I'll study the molecular mass of water, and this is going to be the molar mass of oxygen plus twice that of hydrogen. So I put 2 times 1.007 plus 16, which is that for oxygen, and so on and so forth. So I'll give you an example. The Hope diamond, 44.5 carats, is almost pure carbon. The Rosser Reeves ruby, which is 138 carats, is primarily aluminum oxide. 1 carat is equivalent to a mass of 0.2 grams. Find the number of carbon atoms in the Hope diamond and the number of aluminum oxide molecules in the ruby. So I'm given a particular ruby and a particular diamond, and we want to find the number of atoms in these. So to do so, where does the number of atoms show up? This is capital N. To find this capital N, number of atoms, I've seen it in the number of moles. The number of moles is N over Na, which is the mass over the molar mass as well. Now let's look at the given. What do we have? We have the mass of the diamond. Let's name it MH. 44.5 times 0.2 to convert to grams. I also have the mass of the ruby, 138 times 0.2 grams. And I'm given the molar masses for carbon and for aluminum oxide. What's nice is the molar mass of the aluminum oxide is already given in total, but this was, of course, found by finding the molar mass of aluminum, multiplying that by 2, plus the molar mass of oxygen, multiplied by 3. So yes, I have the molar masses. For the Hope diamond, it's 12 gram per mole. And for the ruby, it is 101.96 grams per mole. So knowing the mass and the molar mass, I can find the number of moles, and then I can deduce the number of atoms, which is going to be the mass over molar mass times Avogadro's number. So I'll just substitute these. 44.5 times 0.2, this is for the diamond, times Avogadro's number, 6.02 times 10 power 23, over the molar mass, which is 12. Now the mass here is grams. This is gram per mole, and this is atoms per mole. The unit will be out, it's gonna emerge as atoms, which is the right unit we're looking for. I have done some calculations here, so you can find the values. Avogadro's number is also given to you in the exam, of course. Any questions? So now we can start our study of an ideal gas and what it means, and we will apply some thermodynamic study of these gases. So before we do our study of thermodynamics on gases, I will make an approximation for an idealized gas to remove some of the interactions that occur. So for example, I'm going to assume an ideal gas, which is basically a low density gas, to minimize the interactions that happen between atoms. Atoms basically in a gas, they will be colliding with each other, interacting with each other through different forces. They will also be colliding with the walls of the container. So we are gonna consider a low density gas to minimize sophisticated interactions that we have. And for our ideal gas, we can start checking different effects of things that are happening in our gas. For example, one thing we notice, and we're gonna study this logically as well, at constant volume, the pressure is proportional to the temperature. What do we mean by that? I have a gas in a container. I heat up this gas. As you can see here, the hot plate was off. The hot plate is medium. What happens is the pressure increases in the gas. This gas is in a sealed container, so it has a fixed volume. What I want you to notice is the pressure increase is due to the motion of the atoms. When you increase the temperature, the atoms gain some energy. And the result is that they will move faster. And if they move faster, they collide more with the container. And here we define the pressure, which is going to be the quantity that's equal to the force per unit area on the container. So the pressure, which is basically due to the collisions, is going to be increasing. The pressure, which is the collision forces over the area of the container, will increase as well. So that's our first observation in a gas. I remind you, we did something similar to this a little bit in solids, where we said when the temperature increases, the volume increases, the area increases, the length increases. So we're talking about dimensions. We didn't talk about pressure in solids because the pressure of essentially is due to some fluid that we have. So solids are not going to be studied in terms of the pressure that they possess. So this is what we name, by the way, Amonton's law, which says that P is proportional to T, or P over T is constant if I have a constant volume and number of moles. You can see our graph here, which shows the linear relationship between the pressure and the temperature in a gas. As you increase the temperature of a gas, its pressure increases. That's all I want you to know, by the way, from this slide, that when we heat up a gas, the pressure in this gas will increase. Now, my second experiment is I'm fixing the temperature and I'm changing the volume. So you can see in my demonstration here, I'm changing the volume in a container. Now what we notice is if the volume increases, the atoms have more space between them, then the pressure decreases. So here, rather than having an increase in the pressure, we have the other way around. Why? Because look at what we have. If there's more space between the atoms, there will be less collisions. So the pressure decreases. So the pressure and the volume have an inverse relationship. P is proportional to 1 over V. So now our right, Boyle's law, which says that PV equals constant when we have a constant T and N. And you can see the relationship between these two, P versus V in our graph here. As the volume increases, the pressure drops down. And the inverse relationship gives us this curved line, basically, because if you plot 1 over x, you have a curved line, right? We can also see our next experiment, which is at constant pressure, V is proportional to temperature. So here, if we increase the temperature, we make sure the pressure is the same, then the gas will be expanding. So the volume is proportional to the temperature. And finally, the pressure is also proportional to the amount of gas. You have a container, you add more atoms, you increase the number of moles of the atoms, the pressure increases. So adding more gas atoms results in the pressure increasing. So we have noticed these multiple relationships, as you can see. The pressure increase can affect the volume, it can affect the temperature increase can affect the volume, it can affect the pressure. We can link all of these experiments together in one law, which we name the ideal gas law. The ideal gas law links all of the previous experiments we studied. So we noticed how P is proportional to T, P is proportional to 1 over V, P is proportional to N. So we combined all of these here and we found there's just one single constant that is variable between them. And our formula will look like this. P, the pressure of a gas, is equal to nRT over V, where N is the number of moles, R is the gas constant, T is the temperature, V is the volume of this gas. So R is a gas constant, it's given to us, it is equal to 8.31. I can also rearrange this equation. It will look like PV equals nRT. This is the well-known ideal gas law. And this law basically tells us a few things about a gas. Namely, if we fix, let's say, all of these, we increase the pressure, definitely the volume decreases. If I fix these three and I increase the pressure, definitely the temperature will have to increase, and so on and so forth. So we have an example here. An ideal gas at 20 degrees at pressure of 1.5 times 10 power 5 Pascal is in a container having a volume of 1 liter. In part A, we want to find the number of moles of the gas. So we want to find N. What are we given? The temperature is 20 degrees Celsius. The pressure is 1.5 times 10 power 5 Pascal. And the volume is 1 liter, which is 10 power minus 3 meters cubed. So usually to find the number of moles, I would think of mass over molar mass or number of atoms over Avogadro's number, right? However, here I don't have any of these as given. So I will have to think about how to use these three to find the number of moles. And this will be through none other but the ideal gas law that I just learned, which says that PV is nRT. So N is PV over RT. P is 1.5 times 10 power 5. V is 10 power minus 3. R is 8.31. And the temperature is 20. Now, yeah, I wanted to notice something. I converted the volume from liter to meters cubed. This is the SI unit of volume. And converting 1 liter is 10 power minus 3 meters cubed. I have another conversion, which is for the temperature. I told you before the SI unit of the temperature is Kelvin. So I'll have to convert this to Kelvin. This will be 293 Kelvin. And so here I can now substitute the temperature in Kelvin and calculate the number of moles. Let's look at the final answer, 0.062 moles. In part B, the gas pushes against a piston, expanding it to twice the original volume. So this gas is in a container, and turns out this container is sealed with a piston, and pistons can be lifted up and down. So this gas expands to twice its volume. So if the piston was somewhere here, this is V initial, then V final is somewhere here, which is twice V initial. The pressure falls to the atmospheric pressure. So, okay, P initial was 1.5 times 10 power 5 Pascal. P final is the atmospheric pressure, which should be given to you in the exam, but usually we use the tables in the book when we're doing problem solving. The atmospheric pressure is 1.01 times 10 power 5 Pascal. We want to find the final temperature. Okay, I'll use the ideal gas law again. PV equals nRT, which means that T is PV over nR. Perfect. We're looking for the final temperature. So this will depend on the final pressure and volume. Now the R is a constant, it will not change. And the number of moles is the same because the container is sealed. None of the atoms escaped outside. So the number of moles must be constant here. Atoms cannot just disappear, which makes things very straightforward. Also substitute P final, which is over here. It's given to me. V final, which is twice V initial. And V initial was 1 liter or 10 power minus 3 meters cubed. And I'll divide that by the number of moles, which we just found in the previous part to be 0.062, and R, which is given 8.314. I can calculate the final. This will be 395 Kelvin. I can find this temperature in degrees Celsius, and I can leave it as it is in Kelvin. That's totally fine, up to you. All right, moving on. So we talked about this ideal gas law. I want to remind you, we assumed that this is a low density gas. We also said that this low density will help us in having less interactions to worry about and less sophisticated interactions when we are studying the atoms of this gas. Well, part of the results of having a low density is that we are going to have elastic collisions between the particles and with the wall. Interaction will be only through short-range forces. When the atoms collide, they make only elastic collisions. We assume all of the atoms are moving in random motion. We assume all of the atoms are point-like. They are just particles and point-like. I don't have any bonds or molecules. I'm just assuming all of this gas is made of single atoms. This helps us in getting the ideal gas law, basically, which we obtained previously. Now, we're gonna also now, in this part, try to link the ideal gas law and the properties of a gas, which are the pressure, volume, and temperature. These are all properties which emerge from the gas atom properties themselves. Namely, I told you that the pressure, for example, is due to the collisions of the atoms with the walls of the container, right? So these atoms, as they collide, they make some forces with the container, and the average force over the area of the container is equal to the pressure. So the pressure is related with collisions that every atom makes. Similarly, for the volume is basically the space that all of these atoms occupy. Now, for the temperature, if we make a thorough study of using the ideal gas law and using forces as well that the atoms are making with the container, we can deduce a relationship between the temperature and the atoms of a gas. So one thing we notice is that we get this interesting relationship that links the temperature of a gas to the speed of the atoms. So how fast the atoms are moving is solely related to the temperature of these atoms. Namely, faster atoms mean higher temperature. And we kind of mentioned that before in earlier slides, where we said if I give heat to a container of a gas, the atoms in this gas will be moving faster. So when I'm giving heat, I'm increasing the temperature and thus increasing the speed of these atoms. Now, one thing I want you to see about the speed of atoms in a gas, there are millions of atoms, even more or less, but there's a lot of atoms that are distributed in this gas. And these atoms don't all move in same speed or direction. In fact, they sort of have a distribution of speed. Some atoms move faster than other atoms, some atoms move slower, but there's a big proportion which have like close speeds, because at the end of the day, these atoms are pushing one another, they're colliding with each other, so they're gonna exchange some speeds. If there's atoms that are too fast, they will collide with the slower ones and give them some more energy and speed. So if we track all of these atoms and we plot the speeds of all of these, like I plot how many, so this graph shows number of atoms having a particular speed. So if you look at this graph, here, for example, the value is 200 meters per second. If you go on the y-axis, we get the number of atoms with the speed 200 meters per second. We can go to 400, check the number of atoms, 600, check the number of atoms with a speed 600, so on and so forth. Now, what we notice here is, if we track all of the atoms in a given gas specimen, there will be a peak in our graph showing us the number of atoms with this speed. Like there's a particular speed which has the highest number of atoms. So most atoms are moving in a particular given speed. What does that mean? It means that we have a distribution of speeds in our atoms. The atoms have varying speeds, but there's a most probable speed that most atoms have. So in the blue graph, for example, the most probable speed is where the peak is obtained. This is at 400 meters per second. If you look at the red graph has the most probable speed at 800 something. What's the difference between the two graphs, by the way? One graph has a temperature 300, the other has a temperature 1200. So what do we notice? The higher temperature gas has a higher, well, most probable speed actually. So the most probable speed was 400 here, it became 800 here. So we have a higher speed for the peak, basically. The peak is basically the most probable speed. We define this as the most probable speed. Now, there's something else I might be interested in for a gas, not just the most probable speed, but maybe I might be interested in the average speed of all of the molecules. We name this VRMS. So we can also define the RMS speed This is basically the average of the squared speeds. VRMS is basically V1 squared plus V2 squared plus V over the number of atoms with a radical. This is the root mean square of all of the speeds. So it's a sort of an average of all of the speeds that we have. So what we notice is this average speed or RMS speed is directly linked to the temperature through this formula. The kinetic energy, the average kinetic energy of all of the atoms is equal to half m VRMS squared, and it's also equal to 3 over 2 kT. Now, we don't want you to know why or the derivation because it's a lengthy study where we start with the forces that the atoms make with the container, and then we move on to show the relationship with the pressure and then the temperature using the ideal gas law. You don't need to know the derivation, but what matters to me is that you can see this direct link between temperature and speed. Higher temperature, higher speed for the atoms, and the other way around. If you look at the quantities we have here, 3 kT and half m, K is a constant. It's Boltzmann's constant. It's given to us. And m is the mass of the gas. So for the same gas, if you increase the temperature, this will affect the speed of the atoms solely. I can also rearrange this equation for VRMS. And you will notice that we can write VRMS as 3 kT over m. Kb and K are the same. They're both called a Boltzmann constant given to you in the test. So we can calculate VRMS using this formula, 3 kBt over the mass. Now, the Boltzmann constant, by the way, can be written as so it has a relationship with the gas constant, which I think we did in a previous slide. Let me look it up. Here it is. So basically, K is equal to R over NA. This is Avogadro's number. So we can write VRMS in terms of R as well, not just KB. So we have these two formulas. In the second formula, we have R as a constant rather than K, but in the denominator, we have the molar mass instead of the mass. So it will depend on what you are given, and then you use the more convenient formula. So let's take a look at this example. We have a gas mixture consisting of molecules of types 1, 2, and 3 with molecular masses M1 greater than M2 greater than M3. Rank the three types according to the average kinetic energy they have. So we have three different masses. M1 is greater than M2 greater than M3, and I want to rank the average kinetic energy. Let's go back to our formula sheet. K is equal to half mv squared equals 3 over 2 kt. So I'll take a look at my formula and I'll check what I have basically. So one thing I noticed, I have different masses here. But if I want to compare K, I need to know what's happening to VRMS as well. And I'm not sure what VRMS is for each one of these. So I'm not sure if I can use this side of the equation, but I can use this side. In this side, everything is constant and my only variable is the temperature. But these three molecules are all in the same gas mixture. All molecules are in same gas mixture. What does that mean? It means that they have the same temperature, and thus they must have the same kinetic energy. So if I want to rank them according to their average kinetic energy, K1 equals K2 equals K3. Now in part B, we want to compare VRMS, the RMS speed. Now I know the RMS speed is basically K times 2 over M, because K is half M VRMS squared, right? I rearranged for VRMS. There's a radical here. K is the same for all molecules, but the mass is different. I know M1 greater than M2 greater than M3. The result will be VRMS1 is less than VRMS2 less than VRMS3. In this question, air is primarily a mixture of nitrogen N2 molecules of molecular mass 28 unit and oxygen O2 molecules of molecular mass 32 unit. Assume that each behaves as an ideal gas and determine the RMS speeds of the nitrogen and oxygen molecules when the temperature of the air is 293 Kelvin. So, okay, what are we given? We are told that air contains nitrogen. Its mass is 28, and oxygen, which has a mass of 32. And we want the RMS speeds when the temperature is given by 293 Kelvin. We want VRMS. I take you back to our formula sheet. In our formula sheet, we said that we have this relationship, half mv squared is equal to 3 over 2 kt. We want the RMS speed, so it's good to use this formula where we rearranged from our first formula here. We rearranged for VRMS. We got 3 kBt over m, or 3 RT over the molar mass. Now, in our question, what's given is the mass, not the molar mass. So I will use this formula, 3 kBt over m. Like we said, K is Boltzmann constant, it's given to us, and the temperature is given, and we have the mass for each of these molecules. So we can just substitute. I'll solve over here. VRMS for nitrogen is going to be radical 3 kBt over the mass of nitrogen molecules, which is radical 3 times Boltzmann constant is given to you. Never mind the unit, it's a bit lengthy. T is the temperature, which is 293 Kelvin, already in SI, which is good. I don't have to convert, over the mass of the nitrogen molecules, which is 28 U. So, by the way, we have to convert this to kilograms. And this is also, it should be given to you. So, I'm going to write it down. 1 U is equal to 1.66 times 10 power minus 27 kilogram. So I'll just multiply by this. And this is our mass. The rest is just calculation. So this should be 511 for nitrogen. You can make a similar study for oxygen. Just substitute the mass of the oxygen molecule instead of the mass of the nitrogen. Any questions? So we have discussed the ideal gas law, where we focused on thermodynamic properties of a gas, and we saw how the temperature of a gas can affect its volume and its pressure. We linked these with the ideal gas law, and we linked these properties also to the microscopic properties of the gas. So we linked the temperature to the speed of the gas. And we can, by the way, yeah, let's get back to our slide. I just want to show you something else. We can also link the pressure to the speed of the gas. We previously wrote down that K is equal to 3/2 kT, right? I can use the ideal gas law and substitute T with PV over NR from the ideal gas law. And then I can get a relationship between PV and the speeds of the molecules. So I can also see this formula, which is for the pressure of a gas in terms of its kinetic energy, average kinetic energy, or VRMS. So what do we have in this formula? The pressure in a gas is equal to the number of atoms over 3 times the mass of the gas specimen times VRMS squared over the volume. This is the volume here. And this is the RMS speed squared. So we have here, we can see a relationship between the pressure and the speed of the molecules as well. We can rearrange, bring this V to this side. We'll get PV equals all of this. And I can write this in terms of the kinetic energy. We have 2 over 3 and K average. All of these are always, as usual, given to you in the exam. We talked about these formulas, and we can finally define the total energy of a gas to be 3/2 nRT. It is the kinetic energy times the number of atoms we have. We name this the internal energy of the whole gas. Here again, we are assuming monoatomic gas. It's made of single particles that are moving randomly. So what I'm gonna go to study next is the zeroth and first laws of thermodynamics, which are laws that govern exchange of energy and equilibrium. Namely, the zeroth law is very easy. It tells us that two systems are in thermal equilibrium if heat doesn't flow between them when they are put in contact. Namely, you can check these two containers, A and B. A and B have the same temperature. If you put A and B in contact and they do not exchange any heat doesn't flow, you don't feel one of them is warmer than the other, then I will say they have the same temperature. Very basic, very easy, and it's actually at the heart of how it's at the heart of how different measurements of temperature work. Now, what we will study next is our first law, which is basically actually an energy conservation law. So to study the energy conservation law, I want first to give you this formula for the expansion of gases. I told you before, if you increase the temperature of a gas, sometimes it can expand and then it lifts a piston upwards, and then it can move wheels and it can operate engines. So here we will say there is work done by this gas. We talked about work in our previous chapter, in chapter 7. We said W is equal to F dot D, right? So I'm gonna use this here as well. And the force here is the force that is exerted by the gas. And the force exerted by the gas is related to its pressure. I told you before, the pressure of a gas is equal to the collision forces over the area of the container. Here, it will be the piston, basically. So I can write F to be P times A. So for the work done, this will be P times A times D. But A times D, which is the area of the piston, times the distance covered, this is basically the volume or the change in the volume if I have a constant pressure. So I will define now the work done by a gas to be the pressure times the change in the volume. Now you can see here I wrote it as an integral form, but you're not required to study integrals in this course. It's just the general formula seen to you. We're going to be seeing the one that I have written for you here more. So let's check out this work done a bit more, and we're going to be using it in an energy conservation law to deduce our first law of thermodynamics as well. So one thing I am doing in this graph is I'm plotting the pressure of a gas versus its volume. We said W is P delta V, right? So if I plot V, pressure versus volume, P versus V, then the area under the graph will be equal to the work done because it's equal to P times V. So if I plot pressure versus volume, the graph I obtain, let's say it's this green line, the area under it is the work done. And one thing I want you to notice about the work done, as the volume increases, this means that the piston is lifted up. This means we have positive work. So I would deduce some positive work done if I have an increase in the volume. And you can see here, I wrote here, W is positive. Check my second process. I have this graph. The volume also increased, which means the work done is positive. In this process as well, well, one thing I want you to notice, let's name this point A. From I to A, V is constant. So W is 0. From A to F, V increases, so W is positive. شوفوا this figure, we are going from F back to I. So the volume decreases, which means that the work is negative. I have two more scenarios. Here, I have the same gas at the initial state. مرة it goes through the green line, and the other time it goes through the red line. And the work done is different in each case. Basically, if you check the area under the green curve, it's going to be much bigger than the area under the pink one. So the area here, this is the work done for the green process. W green is going to be greater than, check the work done by the pink process. It's just this. Because like I told you, it's the area under the graph. So W green is greater than W red. Although the gas starts and ends at the same states, but the work done is different. And lastly, I have this figure which shows a cycle. My gas started here, it goes through a certain process to this final state and then back to this process. So it went through a cycle. And in this case, the work done will be for a cycle or a closed cycle or a closed path. W equals the area inside the cycle. So these are some very important comments on the work done by a gas. We're gonna be checking some examples. I'll work on these next time. For today, what matters to me is that you understand the ideal gas law, PV equals nRT, and then the kinetic theory of gases, which gave us the formulas in this slide, a relationship between pressure and RMS speed, a relationship between temperature and RMS speed, so on and so forth. And then we talked a little bit about the zeroth and first, the zeroth law of thermodynamics and the work done by a gas. Next time we will work on the first law of thermodynamics.